This week, we'll be talking about how to make choices in R, starting with conditionals. Conditionals generate a logical output, true if the condition is satisfied and false if the condition is not satisfied. So common operators, we've seen a few of these before, like the double equal sign, the not equal to with this exclamation point, the less than and greater than, less than or equal to, and greater than or equal to. And it's something we haven't seen before, the word in, surrounded by these percentage symbols. So for example, if we ask R if 10 is greater than 5 and run this line, R will return a logical output. So in this case, yes, it is true that 10 is greater than 5. We can ask the reverse, is 10 less than 5? And R returns an output of false. We can do these with numerical values. We can do this with characters. So is the character string AANG equivalent to this other character string? And that is true. We can ask R, is 3 not equal to 3? And we expect that to be false. And we can ask R, is this character string in the following vector? Oh, and I'll run that, and the result is true. This character string matches something inside this vector. We can combine conditionals using the and symbol or the vertical line for or. So and or vertical line. Let's see an example of these. So we can ask R, is 5 greater than 2 and 6 greater than or equal to 10? And the value false is returned. Let's ask, is 5 greater than 2 or 6 greater than and equal to 10? Right, so at least one of those conditionals is true. And because we have this or statement, R evaluates whether either one of those are true. So a true value is returned. We can also compare vectors of values. So let's create a vector with 5 numerical values, 1, 1, 2, 3, 1, and ask R, are any of those values equals to 1? In this case, R is evaluating that statement for each value to see if it's equal to 1. So R asks, is this first value equal to 1? And it's true. Is this second value equal to 1? Returns a true. Is this third value equal to 1? It returns a false, and so forth. This concept here is the behind the curtain way that subsetting approaches use to subset values. So when we use subset, what we're asking R's, are any of these values equal to some given value? And then it keeps the values where that condition is true. So let's see. an example of this. Let's create a vector called site, and let's store numerical values A, B, C, D. I'm going to run that. Let's create another vector called state, and let's give those the state abbreviations. And one more. And then we can ask our is state equals to FL, so it will evaluate this statement for every value inside of our state vector and returns true, true, false, false. Now let's see our subset site. Let's subset our vector site for values where state equals FL. And when we run this, and it's keeping the values where this is true. So state equals FL, the first and second positions, and when we subset our site, it keeps the values that are true. This would be equivalent to providing a vector where we're specifically telling R to subset site, keep the first two values. And this concept is used in dplyr's filter function as well as other methods for subsetting data. Let's talk about if statements. So if statements are conditional statements that generate logical values as a way to filter your inputs. If statements use the conditional statements we've seen above to control the flow of the program. So the basic structure of an if statement is if, and there's a space in between the parentheses, before the parentheses, the conditional statement is true, and followed by these curly brackets, there's a space here. Curly brackets, I'm going to comment all these lines out. If the conditional statement is true, then do this thing. And then a closed curly brackets. An example of this, let's create an object X that's equal to 6. And let's say if inside my curly bracket, my parentheses is the condition, if this conditional statement is true. So we need to provide a conditional statement. So if X is greater than 5, then do this thing. So let's tell R to calculate X as X raised to the power of 2. All right, so let's go ahead and run this portion and return the value of X. Our X was original X was 6, and our conditional statement was true. So then R evaluated this operation and raised 6 to the power of 2, which 6 times 6 is 36. Let's change X to 4 and run this. So if X is greater than 5, then do this. But if it's less than 5, then R won't do anything. So the value of X is the original value. So this is not a function. So everything that happens in the if statement influences the global environment. If we return to some of the earlier exercises that we were doing, we could now use these if statements to calculate different mass calculations for different vegetation types. So let's create an object called veg type equals tree and some volume. We'll give it some value of 16.08. And now we can say if veg type equals, notice I'm using those double equal signs, equals tree, then do this thing inside the curly brackets. So calculate mass as 2.65 times volume raised to the 0.9, and then return the value of mass. So I'm going to run all of these commands, and the value of veg type did equals tree, so this conditional statement was true. So then R proceeded to calculate the command inside the curly brackets. And so our mass value returns this modified value. In this example, you more frequently want to choose one of several options. And you can add more conditions and associated actions with the else if statement. So let's change our veg type to grass, and we'll keep the same value of volume. And now we want to tell it, okay, well, if veg type is equal to tree, then do this. We've got our closed curly bracket. And then we need to do another condition on the same line as that closed curly bracket. We want a space and an else if, followed by a space, then the parentheses. Else if a vegetation type is equal to grass, and it has a similar format, we expect those open and closed curly brackets. And inside those curly brackets, we tell R the other calculation that we want for it to do if this other statement is true. So we have a slightly different formula to calculate mass if our veg type is equal to grass. So now I'm going to expand this a little bit. We've changed our veg type to grass. I'm going to run all of this. And now our mass is calculated using this second equation. So R is internally checking the first condition. If it's true, it runs that condition's code and skips the rest. If it's false, it checks the next one until it runs out of conditions. And you can specify what to do if none of the conditions are true using else on its own. So similar to our position of else if, we want to position else on the same line, and we need those curly brackets. So if none of these conditions are true, else set mass equal to NA. So let's change our veg type to shrub to see this in action. When I run these commands, I expect a value of NA because I'm not telling R how to calculate mass for this condition of shrub. Let's combine multiple ifs and compare multiple ifs to else if. Multiple ifs check each conditional separately and executes code of all conditions that are true, whereas else if checks each condition one by one and executes code for the first condition that is true. If we see this in action, let's assign x a value of 5. And I'll make this a little easier to read. Let's say if x is greater than 2, we need those curly brackets, evaluate this thing, do this thing, x times 2, close curly brackets. On a new line, we can write if x is greater than 4, then do this thing inside the curly brackets, x times 4, closed curly brackets. So we've got x equals to 5. I'll clean this code up a little bit. Oops. So if x is greater than 2, then calculate x times 2. If x is greater than 4, then calculate x times 4. So let's calculate this. So we've got multiple if statements and they're evaluated one by one, right? So this first one, if x was greater than true, that's true. So R calculated x times 2 and returned a value of 10. And then it evaluated the next if statement. It was x greater than 4, that's true. So it also calculated x times 4. So 5 times 4 is 20. So these multiple ifs are being verified separately and executes code of all the conditions that are true. So let's compare this to the else if. And I'm going to copy and paste and reduce a little bit of typing. So if we'll keep x the same value of 5. If x is greater than 2, then evaluate this. And now instead of my if, I want an else if. Else if x is greater than 4, let's do this thing inside the curly brackets. So now I expect, with the if and else if statements, else if checks each condition sequentially, so in order, and then executes the code for the first condition that is met. So in this example, R will stop evaluating these multiple else if statements when it hits a condition that is true. So let's see an example of this. And I expect x to be a value of 10 because it met the first condition that was true, and so it evaluated this this code and then ignored the rest. So that's something to keep in mind. At some point, you may want to convert your multiple else if statements into a function. Let's create a function called estMass to estimate the mass of these different plant types. Remember, we used the function And remember that inside the parentheses are the inputs. So we want the user to input some value for volume and some value for veg type. And then I need my open curly brackets. And I want to tell R if the veg type input is equal to tree, then do this, right? I've got my open curly brackets. Calculate mass as 2.65 times volume raised to 0.9. Else if, on the same line as this closed curly bracket, else if veg type is equal to grass, curly brackets, do this thing inside the curly brackets. Oh, here, I'll raise this a little bit. Calculate mass as this equation, this different equation, 0.65 times volume raised to 1.2, closed curly bracket, else I need my curly brackets, do this thing. So I want to print, if none of those conditions are met, print. I don't know how to convert volume to mass for that vegetation type. And then I also want to calculate mass or assign an NA to mass. So I'm closing the curly brackets and I want this function to return the value of mass, and then I'm closing the function. All right, so I've written it, but I haven't run it, and I'm going to run it. And notice that it doesn't do anything. Remember, running a function stores it in your global environment. So there it is. There's our function. And now to run it, we need to call the function by its name. So smass. And the inputs are volume and veg type in that order if we don't explicitly name the argument. So the first argument smass expects is volume, so 1.6, and my veg type is tree. Right, so internally, R is evaluating these if statements, and once it gets to the condition where veg type equals tree is true, then it's using this code to evaluate, to calculate mass, and then it's returning the value of mass. So let's do the same thing for grass. So we have a slightly different value because R internally is evaluating this statement. Is veg type equal to tree? False. So it continues to the next condition. Is veg type equals to grass? True. So it uses this different equation. And then it returns the value of mass. What happens when we provide R with a veg type that we didn't specify in our function? It returns the else output, right? So we told R, if none of these conditions are met, print this statement and assign a value of NA to mass. And then the function returns the value of mass, and here it's NA. I know how difficult it is to think about functions when you're first becoming familiar with them. There's a handy tool in R that will create functions for you based on code. So if we were to, let's say we had built a multiple else if statement, right? And this is perfectly valid. If we highlight our code, select Code, Extract Function, provide a name, so I'll give it the same name, smas2 maybe, to distinguish it from the first function we created. R will automatically pull out the input, which is veg type and volume, and create the function from the code. So notice how it added the name, it added this part here based on the inputs that were provided that it expects in this multiple else if statement, and adds the open and close curly brackets. And notice if we wanted to return the value, we would have to specify that. Return the value of mass. So pretty handy. Let's talk about nested conditionals. Nested conditionals are useful because sometimes decisions are much more complicated, and you can nest conditionals inside of one another. Let's see. I want to copy our function, and I'll call it smast again. Instead of these inputs, I'll replace it with volume, veg type, which were the same but a different order, and age, because maybe obviously biomass of a plant can vary by its age as well as its veg type and volume. So I've got my open. So if veg type equals to tree, and I'm going to nest another if statement inside of this tree. So if veg type is equal to tree, then check if its age is less than 5. And I'm going to be very careful about my open and close parentheses. So I'm actually going to move this inside and maybe clean up everything with hard returns. So if age is less than 5, then calculate mass as 1.6 times volume raised to the 0.8, closed bracket, else I'm still inside my age. If age is greater than 5, then do this thing. Mass, calculate mass as 2.65 times volume raised to the 0.9. Right, so if here's a nested if statement, is saying if this condition is true, so if age is less than 5, then do this. If this condition is false, then do this. And then we're back to, that's all inside our veg type equals tree. So now I need to close my parentheses. I need to make sure that my curly brackets are closed. Now I'm ready for the else if. And I think there's an extra Yeah, I think there's an extra curly bracket here. Okay, so now I've done my accounting. So if veg type is equals to tree, do this and check for the age. If veg type is not equal to tree, then evaluate this. If veg type is equal to grass, but now maybe I want, or veg type equals to shrub. I've got my open parentheses. Do this code, mass 0.65 times volume to the 1.2. I've got my closed curly bracket, else, open curly bracket, and then I'll retain this statement and assigning a value of NA to mass and return mass. All right, so you can see how the conditions can become first nested, right? We're nesting another condition inside our veg type. And you can also see an example of where we use that and or. Right, so I'm going to run this and overwrite our existing function called estmass. And now let's run that function estmass. And now we can see there's 3 arguments. The first one is volume, tree, and let's give it an age equals to 2. And so now internally R is evaluating if veg type equals to tree, then it used that, and age is less than 5, then it's using the equation that we provided. Let's calculate estmass, another example for shrub, and age equals 5. And so it's evaluating, is veg type equal to tree? That's false. So then it continues to the next condition. Is veg type equals to grass or shrub? And that is true. So then it's using the provided code. Nesting is clearly difficult to follow, right? You can see I was making sure I was accounting for all my closed and open curly brackets, and it can be difficult. So it's good to know how to do it, but it's also something that we should minimize if possible. When working with conditionals in R, sometimes you get an output of false when you expect true, and that's because of something called a floating point. Let's see an example of this. Let's assign x a value of 1.3, y a value of 2.8, and let me run these, x, y, and then let's calculate x times 2 plus 0.2. So x 1.3 plus 2, so that'll be 3.3 plus 0.2. Let's ask if is this equal to y? That's x times 2, so that's 2.8. So we're asking, is 2.8 equal to the value of y? And y, we assigned a value of 2.8, so we expect a true, right? Let's evaluate this conditional statement, and R returns a value of false. So what's going on? Because 1.3 times 2 plus 0.2 is equal to 2.8. Right? So this should be a cue that there's something happening internally. And it's this, right? You get this unexpected results from some arithmetic. And that's because R includes a very small trailing digit. You can see this better in Python. So I'm going to see if I can bring up a browser-based Python shell without having to install it. It's quite useful. So let's evaluate now 1.3 times 2 plus 0.2 equals 2.8. And again, we receive the value false, but now we can see why. 1.3 times 2 plus 0.2. I left out a 2 plus 0.2. And now we see this very small trailing digit at the end that is appended when you're using programming languages. So to avoid this, we often use the round function. If you come across this, the solution is to use the round or all that equal functions. So let's testing equality with decimals. You will need to use the round function so that you explicitly tell R to cut off those trailing digits. So x times 2, the same equation from above, times 2 plus 0.2, and the round function expects, right, the number and then the number of digits you want to round to. So now we're being explicit and saying drop those trailing digits. We can also use all that equal. So x times 2 plus 0.2. So this creates, right, this evaluates whether these two arguments are equal. So now, if I had stored this as something called x2 and evaluated is x2 equal to y, now we receive the expected true. As we move to more advanced concepts where we're working with functions and else if statements where there's a lot of these parentheses and curly brackets, and it's a lot of complexity, style if your code becomes very important. You want things to be readable, you want to use the same style consistently, and you want to use the same style as others. Oh, part of our reading for this week is the recommended style guide. And some of those recommendations, let's talk about style. Some of those recommendations are white space. I try to be good about this, but there's some instances where I don't include white spaces when I'm working. So indentation is what the brain recognizes, and it's used regardless of the language or braces. So what's recommended is two space indents. So let's look at stuff, data, and when you do a hard return, it automatically does the spacing. But we could compare this to no indentation, and it's kind of difficult to keep track of everything, right? So instead, we want those indents. Oopsie. We want those automatic indents to make it nicer visually. You also want to include spaces after commas and around operators. So for example, you want a space after your comma and you want a space between your operator. Right? That having the space is a lot easier to read than when there's no spaces, especially if you have lines and lines of code. You want to make it as easy to read and understand the code as possible. Other recommendations for naming include something called snake case. So that is when you use this underscore to combine two words because that's easier to read than a single word altogether. I think using the snake case is a little bit easier to read than something called a camel case, where your first word is lowercase and your second word is capitalized. I think it's right. I mean, let's compare these side by side. You can see this is a little bit easier visually to process than camel case. You also want your naming to be descriptive. So, what the function is doing, estimate biomass. And you don't want it too long. You don't want something like estimate biomass using Hansen method, right? It's too long and the rest of your code isn't going to fit on the same line, and so it's going to be difficult for your eye to follow. And we have been using abbreviated words like est mass or est veg type. In most cases, you want to use whole words for accessibility, especially if this is code that you're going to leave behind in your lab for future students to use. You want to use the whole words. If your code is something that you think only you will use and not pass it along, then use what you understand. But if this is something that could possibly be shared, then use those whole words. Another recommendation is what to do about long lines. You want lines less than 80 characters long because that's what pretty much fits in a single window in R when you're working inside RStudio. You can add an indicator line, which is really useful. To do this, we go to Tools, Global Options, Code, Display, and we want to show margin. And you can select the number of characters. So here I've got it set at 80. And there should be, and if I zoomed out a little bit, then you can see that 80 character line that appears. The final style recommendation is for long lines is that if it's clear that a line isn't finished in R, then it will go on to the next line. And sometimes that can affect the visual clarity. So let's create I'm doing this all wrong. I'm going to copy and paste a several lines long, and then I'm going to maneuver the length to try to demonstrate how the lines change. To demonstrate this in our studio, I had to hard return right here. But R understood that as if I did a hard return, R understands that this line isn't complete. And so we'll read it as one single line. So we'll understand, even though this occurs on two separate lines. But you want to avoid this. Instead, you want to try to do a hard return in where there's like a comma or a closed parentheses. And R will automatically reformat your code. It should be code, reformat code, and it's a really nice functionality of R.